All right, we're looking at Chapter 10 assignment, Problem 6. We are given information about the customer satisfaction survey results for two different consultants, where maximum is the maximum service rating is 7. So we have a more experienced consultant with 10 years of experience and a relatively new consultant with 1 year of experience. Using an alpha of 0.05, we want to know, is there any significant difference between these two ratings? So we're looking at a hypothesis test of the difference between two means, mu sub 1 minus mu sub 2, and because we want to see if mu sub 1 is greater, that's our hypothesis, we want to be able to conclude that the rating for the first consultant is greater than the rating for the second consultant, which means that the difference would be greater than 0. And therefore, the null hypothesis would have the difference to be less than or equal to 0. Less than being maybe consultant B has a higher rating. But assuming they're both equal, less than or equal to 0. So we compute the test statistic, and I'll show you how we do that in a moment, to 2 decimal places, 1.99. Then they ask, what is the p-value? Now, with this test statistic, or this calculated t-value, what we're using here is a t-value because we don't know the population standard deviations. We simply have the sample standard deviations. That's your clue that we are using a t distribution instead of a z. And with that, the best we can do is, if we're using the tables anyway, is to determine the p-value within some range. So they're asking you to select that range. You have to calculate the degrees of freedom, which they don't ask for, but they want you to recognize that you have to calculate that really hairy degrees of freedom equation in order to answer part C. Once you've done that, then you can conclude that you do have significant evidence at a alpha of 0.05 to reject the null hypothesis and conclude that the difference is greater than 0. So the consultant A's rating is significantly higher than the consultant B rating. Of course, we're using pretty small sample sizes here. But that's the conclusion. Now, you can either do this manually, and of course, if you do this manually, these are the two equations that you would need to use. This is the equation for the t-value. This is the equation for the degrees of freedom. Neither one looks very nice. And believe me, I know from personal experience, because I tried it, it's not much fun. This is my calculation for the degrees of freedom. So obviously, programming this into Excel is a lot easier. Now in the textbook, they have a function in the data analysis toolkit that you can use, but that's only good if you actually have the raw data. We don't have the raw data. The file that you are given for this problem just summarizes the same information in the problem itself. The sample size, the sample mean, and the sample standard deviation. But if you do go through this calculation, remember that when you get to the end, regardless of the decimal portion on the degrees of freedom result, you should round down because that's the more conservative approach to take. So even the 16.9 that you'll get through doing all this calculation should be rounded down to 16 degrees of freedom. But let me show you how to do this with Excel, because in my opinion, it's the only way that makes sense. But it's worth doing this at least once so that you understand why learning Excel is worth the effort. So in your Excel toolkit, and this is version 40, Stats Toolkit 40, I've constructed 3 different tests: a one-tail test for a lower tail, one-tail test for the upper tail, and a two-tail test. You can disregard the information in the one-tail, lower tail test and the two-tail test, because what we're looking at in this case is an upper tail test. We want to know if that difference is greater than 0. So the hypothesized difference in this case is 0. And I put in the information for the 2 sample sizes and the sample means. It calculates the point estimate of the difference. I left this in because this value is useful if we were going to calculate the confidence interval. In this case, we're not, so this value is not used. And we input the standard deviation for samples 1 and 2 and our level of significance. It calculates the confidence coefficient, which again is not used in this particular calculation. Here's the hard part: the degrees of freedom. I've broken the degrees of freedom calculation into 2 parts. The numerator, so make a note, if you want to program this yourself, this is the degrees of freedom calculation for the numerator. And for the denominator. As you can see, this is a pretty scary looking set of equations. And I may have extra parentheses here, but I do that just to be safe. So it gives us 16 degrees of freedom. We take the ratio, the numerator divided by the denominator, 0 decimal places, and we want to round down whatever the decimal portion is, which gives us the 16 degrees of freedom. We calculate the t-value using that t-value equation. You can pause if you want to see how I've done this. And then we also take the absolute value to determine the critical t-value. And I use the absolute value of the critical t-value if I want to compare the two. Because we're doing an upper tail test, I want to use the t-distribution for the right tail using the degrees of freedom and the calculated t-value to determine the p-value. And again, as you can see, the p-value is between 0.025 and 0.05. And because it is less than our level of significance, we can reject H sub 0 and conclude that we have enough evidence to indicate that the customer ratings for consultant A is in fact greater than the ratings for consultant B. So we can say that our more experienced consultant did receive higher ratings, even though on the surface the difference in those ratings was just 0.57. So I will upload this final version of the toolkit so that you can use it to solve these types of problems if you choose to. To coincide with the example given in your book, if you load the data analysis add-on, if you had the actual data, then you would use the t-test 2 sample, assuming unequal variances as the tool you would use. But again, you have to be able to define the range for the first and second variables, a hypothesized difference, and then simply put in place the output range or where you want the output to be placed. But that only works if you have the data. If you don't have the data, but you have the summary information, you can use this tool.